what we're going to talk about tonight is first kind of presenting remote attestation in the context of confidential computing, why it's needed. Then talk about the framework of secure remote attestation, what makes it secure or what makes it insecure. And thirdly, we'll talk about two specific challenges that we've had to overcome when we built our product on top of confidential computing.
Sorry, Gaëtan, are you sharing the screen?
Yes, I am. Not anymore.
I think there was some kind of connectivity issue.
Okay, it's backstage. Cool. Thank you. So what is the value offering of confidential computing when it comes to security? The value offering is to essentially go back to the good old days of computing, where you self-hosted your hardware and you control the entire stack running on top of it. Of course, now one of the most favored way to deploy code is to use cloud computing, where a cloud provider is going to handle all the manageability and scalability issues for you. But it came at the expense of security. You had to trust the cloud provider with your data, essentially. So confidential computing offers you a way to take advantage of cloud computing while still keeping the strong security guarantees of self-hosted, completely controlled platform. And the way it does that is through remote attestation. Through remote attestation, a verifier can ensure that a remote system complies with its trust model, that it's running a secure chip that is configured securely, and that all the software, the workload that has got access to confidential data is secure, and so that it will enforce the confidentiality and the integrity of the data. So remote attestation allows you to enforce your trust model on a remote system. This is really cool technology, and it allows us to build really cool use cases. For example, at Decentriq, we're developing a product that is running a data clean room on top of confidential computing technology. And this data clean room allows two mutually entrusted parties to collaborate on data without sharing the raw data. So a pharma research company can perform analysis on patient data owned by a hospital without ever accessing the raw data. And once again, it's enforced through remote attestation. Both the hospital and the pharma research company are going to check that the entire software that is deployed is secure, and the hospital can also check exactly which query is being computed on the data, and check that it's not going to leak any privacy sensitive information. To develop that product, we've worked with confidential computing technology for many years. We are an early adopter of SGX, integrated both the EKID and DCAP protocol. To my knowledge, we are the first to have deployed AMD SCV-SMP in production, and we've also integrated the Nitro, but are not using it in production anymore. Now let's talk about how to assess the security of a remote attestation scheme. These are mainly the three properties we cared about when we looked at Nitro, AMD SCV-SMP, and SGX. The first one is comprehensiveness and the interpretability of the evidence we get from the system. We need to know everything about our system that is security relevant. So we need to know all the configuration of the hardware, and we need to know everything that's about the software that's going to touch the data. And that evidence that we get out of the remote attestation system needs to be interpretable. It shouldn't be just an opaque blob that we can't tell what it is. This evidence that we get should also be valid at the time of verification. So we need some kind of timeliness or freshness system. And finally, the mechanism by which attestation is performed should be trustworthy. So for example, in CC, the attestation that is measuring and reporting evidence is performed by the chip firmware. And we need to be able to assess whether the chip firmware is vulnerable to, is in a version that is vulnerable to some attacks, or whether we're running a trustworthy version of the attestation firmware. So now I'm going to let Andras talk about those specific challenges when we wanted to enforce these three security properties with current CC tech.
Thank you. So I want to elaborate a bit on exactly what we're looking for when we're looking at an attestation scheme. The goal of attestation is really to present this evidence, the attestation evidence, to the client, which proves that they're talking to an isolated piece of code that's been loaded into a secure environment. And then they can make a judgment call on whether they trust that system or not. So what are we looking for concretely? So first and foremost, we're looking for the measurement or the hash of the binary that's been loaded. In and of itself, this hash is just a hash. So we also need a way to bind that to the actual source code that the executing enclave or isolated code is executing. Furthermore, we need the hardware vendor to sign over the measurement and actually every piece of evidence that we get from the computational computing system. This needs to be the hardware vendor, and I'll go into a bit more detail later on why this is. So the second thing we're looking for is some kind of versioning scheme of the technology that we're using. So in this case, we're calling it TCP version, Trusted Computing Based Versioning. This includes various components of the technology, like the microcode or perhaps a firmware version. Basically, a versioning scheme which allows us to reason about the state of the technology. The reason we need this is, over time, there are new vulnerabilities discovered, there are new versions of the firmware being released, there are new versions of microcode being released, and these have different security properties, and we want to be able to differentiate between these. However, we have a similar issue as we have with the measurement. If you're just looking at a version number, or in the case of SGX, for example, you're looking at CPU SVN, which is an opaque blob that represents some kind of versioning scheme, we cannot discern what that actually means. So we need also a third component, which is some kind of appraisal of this version. What does appraisal mean? This is an evaluation of whether the specific TCP version that we're talking with is secure or not. Are there any known vulnerabilities? Is the hardware configured correctly? So these are things that we cannot discern ourselves, and the only entity in this picture which has enough information to do this is the hardware vendor. So, and this is because they get all the vulnerability reports and the responsible disclosures from security researchers. They're the ones that are rolling out mitigations against this, and they're the one that can actually bind together the version number with this idea of whether it's secure or not. So how does this look like for actual technologies? With Intel, well, Intel SGX specifically, we haven't looked at TDX yet. So with SGX, we basically had the full package from the get-go. There are two protocols, or rather sets of primitives that Intel exposes. One is called EPID and the other one is called DCAP, as Gaëtan mentioned. If you look at the details of these, they look quite different, but if you take them apart, you will find each and every one of these properties that we're looking for. So how does this look like for AMD SCV SMP? Well, we have the first two. So we have the measurement included in the attestation evidence. We have a versioning scheme exposed, starting with SMP. So that's the first one that actually has a versioning scheme in the evidence. But we're missing the appraisal bit. If you're looking at these version numbers, they're really just numbers. Okay, I think I lost connectivity. Sorry about that. So I'm not sure where I was, but basically with AMD, we get opaque version numbers, and we cannot really assign meaning to them. So we don't know whether a particular version is vulnerable to certain exploits or not. So what did we do to work around this? We basically burnt into the verification routine for these attestations the exact version numbers that we're expecting, or either the minimum version numbers that we're expecting, and we try to keep this up to date. But obviously this is not ideal. It is transparent in the code, so our customers can look at these numbers, but they also don't have enough information to actually evaluate what these numbers mean. So this is something that's simply missing from the SMP attestation evidence currently. The next technology that, actually we integrated AWS Nitro before SMP, but with AWS Nitro, we have a very different situation. In the Nitro attestation evidence, we do get the measurement. They're calling it PCRs, but the whole versioning scheme is completely missing, and there's a reason for this. In the AWS Nitro threat model, the hypervisor is completely trusted. So what this means is that on one hand, they don't need to really expose any kind of versioning scheme in the attestation evidence, but on the other hand, it's a weaker threat model. So you need to trust Amazon. And when I say trust, I don't necessarily mean that you need to that Amazon engineers are not doing their due diligence. I mean that you trust that an attacker cannot take control over Amazon resources. They cannot take control over the hypervisor, and maybe that's good enough for your particular workloads. But for our customers, that wasn't good enough, and that's the main reason that we switched away from it. But it also has some redeeming qualities. For example, the programming model is I think really nice, and I want to particularly point at the VSOC abstraction. I think that's the way to expose the comms channel between the host and the guest VMs, and we actually implemented it for SMP as well. So I also wanted to mention a kind of trend that it keeps popping up, and I wanted to just mention that we don't think this is a good direction, really. There are some projects by CSPs that are sort of replacing the root of trust in these attestation schemes. So they basically inject themselves as a root of trust in place of the hardware vendor. And we don't think this is a good thing. the reason is that, well, we already need to trust the hardware vendor with these technologies we are using. I mean, these cloud providers are using these hardware vendors' hardware. So now we need to trust. If they do replace the root of trust, then we need to trust two entities now instead of just one. So, and there are other ways that they could add themselves, the CSPs, to the attestation evidence, which isn't as dangerous. So, for example, they could provide endorsement signatures that are on top of the attestation evidence, which prove that, or which show that the piece of hardware that you're communicating with is actually in their data center. So that would be a way to add themselves to the attestation evidence, but not replace the root of trust. So we talked about how an ideal attestation scheme would look like, and I wanted to zoom in on one particular aspect of it, which is this binding between the measurement and the source code. So at the end of attestation, actually, I'm not sure whether we have enough time to go over this. So maybe I'll try to speed this up a little bit. At the end of attestation, what we really want to end up with conceptually is a communications channel between the client and the isolated code. And this should be an end-to-end encrypted channel. It should be authenticated. So you can think of attestation as a sort of authentication scheme for the remotely executing code. And when we think of authentication, we think key pairs. So the best way to conceptualize this is that the enclave should be a holder of a private key, and the public key corresponding to that should be signed over in the attestation evidence. I'm not going to go into too much detail here. I just want to mention that when you're looking at the evidence that is presented to you during attestation, it's still just a bunch of blobs. So there's a measurement, which is a hash, which is a blob. There's the report data, which might include this public key, but you don't actually know whether that's the case. The way to establish that this is the case is if you have access to the source code, and this is where the next big requirement comes in. You can reproduce the build. So it's not enough to just have access to the source code. You need to also be able to reproduce completely the binary or the VM image that you're loading into these environments. And this should be bit level reproducible. The two projects that we're working with, which enable us to do this, are Nix and the Debian reproducibility project, which is a set of tools that allows us to reason about reproducibility. The other side of this, which is also needed, is, well, even if you can reproduce the build and reproduce the measurement, you still need to understand what the code is doing. The code could be doing something that it's not supposed to. It could, for example, not generate that key pair that we're talking about. It could just take it from some untrusted source. The way to make sure this is not the case is to actually look at the code and construct a mental model about what's going on. And this is where auditing comes in. What we've seen our customers do is that, well, we cannot reasonably expect every customer to look at the source code. And instead, what they tend to do is pay auditor companies to do this for them. So that's kind of the trend that we're seeing. Actually, I think that this is the auditing part is the most complex bit in the attestation scheme, and actually probably in the confidential computing scheme. I don't think that it's talked about a lot, but it is really, really complex. And we could spend another hour or two just talking about that. Yeah, next slide.
Cool. So the last thing we're going to talk about that we think needs some love in the confidential computing space is about the physical security of the chip. In reality, in confidential computing, we have some partial trust into the party that's hosting the chip, because the chip is vulnerable to advanced physical attacks. So we're talking about an attacker that will be able to sneak in a data center with all his tools to be able to open the box, the server rack, connect its tools to the hardware, and then run something like a glitching attack with the power, etc. So quite an advanced attack. The problem at the moment is that these attacks are possible in unsecured and trusted environment. But there's actually no way for a verifier to tell the difference between a chip that's running in the secure data center with guards and dogs, etc., or a chip that's running in my garage. What we're doing at Decentriq is that we're because we care very much about that problem, we've been pinning in the verification procedure exactly which chip is allowed to run our platform. So this mitigates the security issue. It comes with its own set of problems. It doesn't scale mainly because it puts a lot of burden on the verifier, and it also breaks the cloud abstraction where we need to have access to the specific hardware when the cloud is trying to abstract that usually. So the discussion we'd like to open with the community is whether we could look into this strong proof of chip ownership or physical locations, whether we can tell if a chip is in a secure data center or not. We've seen that AMD may be looking at that with their latest ABS specification for SEV-SMP with the VLEK, but it's not clear exactly what's the use case for that key. We know it's controlled by the cloud provider, but we don't know how it's provisioned exactly. So if we could get more information on that, it would be cool. The second way I see we could go would be to look at the trusted computing group specification, which has looked quite a lot into the security of the hardware supply chain. So being able to source where the hardware is coming from and going to. I'm thinking especially about the TPM, Trusted Platform Module, and the platform certificate work. So if anybody would like to talk about it, we are there.
So hopefully the main takeaway to take away from this talk is that attestation is quite nuanced, it's quite complex. And actually all this nuance is encapsulated in a very particular piece of code, which is the function that verifies the attestation evidence. So if you're looking at one function that's extremely important in any kind of CC system, it's that function that verifies this evidence. It will literally go over every single guarantee that is checked or should be checked. And this is also why we think we're just putting this out there. It would be nice if there was a community maintained public open source library that does this verification, some kind of standard. And then this would be something that security researchers can look at. It's a single place to harden all the verification, which is now essentially implemented by each and every CC company separately. So that would be nice. Yeah, that's the talk. Thank you for listening.
Thank you.